Hello class. So for today's lecture, I would like to compare the false position method code and walk you guys through the code with bisection method. Okay, so first thing, let's go ahead and define our X spacing. We'll do 100 points, and then let's define our function that we're finding the root of. Log of X plus minus 3. And actually we need to go from 0.1 because of this natural log here. And so then let's go ahead and plot and look at where our bounds are going to be. It's the power of the graphical method. And let's just save it as false position method versus bisection method. Oh yeah. Make sure you put in your anonymous function the input arguments. Okay, so let's choose bounds negative 0.5 and 0.5. Or actually it looks like 0.6, and we can choose like 0.9. So we'll say x lower equals 0.6 and x upper equals 0.9. Okay, and that's a pretty reasonable bound. And so let's go ahead and evaluate the false position method. Okay. And so we'll define this we'll call this I-val equals x lower and x upper. Okay, and we'll write a function. So, and what we're doing in this is we're going to have two outputs. We're going to have the root, and then we're going to have the iteration. And we're going to set this equal to false position method. We're making a function, of course, and we're going to input the anonymous function. We're going to input the bounds, and we're also going to input the X spacing. Okay, so this is a function for the false position method. Input anonymous function. And the optimization, this would be called like the cost function. So we can kind of refer to this as kind of the cost function. Anonymous function, the interval, and the X spacing. And then we'll output the root and the iteration. Okay, so the first thing we want to do is go ahead and define the error. Say it's 1, the max error as 0.001. Do 1 times 10 to the negative 3. We'll say the iteration starts at 1, and then we'll say the maximum iterations equals 500 to prevent the for loop. Okay, so now let's go ahead and define our x lower as I-val of 1, x upper equals I-val of 2, and then let's use the false position formula. x upper plus, go ahead and put parentheses, f of x upper times x upper minus x lower divided by f of x lower minus f of x upper. And make sure you put in, because we defined the function as fx, do fx. Okay, so this is a false position formula. So this is our initial estimate of the root. And so we'll say while EA, or while the error is greater than max error and the iteration is less than max iteration, then we are going to evaluate and loop through this. So the first thing, let's go ahead and do our conditional statements. And these conditional statements, again, are identical to the conditional statements for the bisection method. So these methods are closely related, except in how you are approximating the new root. And if you refer to the derivation file, then you will see how they, like, the mechanisms work a little differently in that, of course, and as we talked about in lecture, false position method uses the principle of similar triangles to obtain the root, and then the bisection method just cuts the interval in half. So this will be f of x times xl times x lower, because we're using x lower as a reference. Then we're going to evaluate at the root. We're going to say if it's less than 0, then we're going to shrink the upper interval. Else if f of x of xl times f of x of xr old is greater than 0, then x of l equals xr old. We're going to shrink the lower bound, else the root equals xr old. Okay, now let's go ahead and evaluate the new root, and let's just copy and paste this formula up here, this equation. Now we need to evaluate the error, equals absolute value of xr new minus xr old divided by xr new. And then we'll define xr old equals xr new and increase the iterations. Iteration equals it plus 1 and end. And then we'll say that the root outside of the for loop, the root equals xr old, and then the iteration equals it. Okay, and now let's go ahead and, well, let's cut this and paste it before this section. So this will be the false position method. And then we can do the bisection method. And what's amazing is we can literally copy this entire code for the false position method. And you guys can do this on your homework in problem 1 to compare the number of iterations and compare the speed of each method. That way you can get the fastest code. So we'll call this BIS. BIS, we're feeding in the same information for bisection method. And all we have to change in the bisection method code is how we're evaluating this interval. So all we're doing is cutting it in half. X upper plus x lower divided by 2. And then it's going to be the same thing. So you just copy, paste this. This is supposed to be absolute value. Okay, so now let's call our functions. So we're going to say the root of false position method and iteration of false position method equals FPM of fx and ival and x, and then we're going to call root of bisection method and it of bisection method, and we're going to do bisection method fx, ival, and x. Okay, and actually let's not suppress these, or okay, we can suppress this and then print it to the command window. Root from false position method is percent 0.2f, and the iterations is percent d, and we'll do /n, no space here. And then the root from bisection method is percent 0.2f, and iterations of iterations. Actually, let's just do /n here. Okay, and then we're going to feed in root of false position method, it of false position method, root of BIS, and it of BIS. All right, and let's go ahead and run it. Line 31. All right, max IT. All right, change this FX. You got to change it in this code. So as you see in this function that we're evaluating, the false position method evaluates it in 3 iterations, and the bisection method evaluates it in 9. So in this case, because this function is well behaved, in terms of it has a smooth, and the false position method does not get stuck, then the false position method evaluates it more efficiently. And so let's just compare what f0 gives us, fx, and initial guess we'll do 0.7. Okay, so if we round this answer, oh yeah, okay, 2 and 0.68. So we have 2 numbers to the right of the decimal, and so the roots are correct. And again, in this case, the false position method evaluates it faster. So I will see you guys either in class, or if I post another video, I will see you guys in the next video. I hope this helps.